We now have our lightning talk sessions, which are pre-recorded 3-minute presentations, and they talk about 10 projects on different topics related to CBK. And you can find the abstracts for these talks and those accepted for publication, and they're available in the MCBK meeting login and instructions and meeting tips email that you received, and they're there on the MCBK website. So after listening to these talks, you need to choose which Zoom meeting you want to go to. There are Zoom meetings specific to each talk so that you can ask that particular speaker questions. And you're free, and in fact we encourage you to move around and attend various of those Zoom meetings. So now we'll head off into the Zoom session.
Health and social care systems throughout the globe are currently undergoing massive organizational, technological, and methodological paradigm changes. Regarding the methodological paradigm change, we are moving from empiric phenomenological medicine addressing humanity by observations, pattern recognitions, creating data through evidence-based medicine, referring to group-specific treatment outcomes statistically evaluated, towards person-centered medicine, addressing the individual, and process management care using for cross-communication terminology standards and process standards towards personalized medicine, addressing the individual and personal disposition based on the knowledge, representation, and management of the different disciplines involved. Finally, moving to P5 medicine, we address the individual and personal, environmental, social, and occupational context, using scientifically justified individual status information, creating a knowledge space to be managed. For managing such complex systems of systems, we have to formally represent them, addressing the different domains and their representation using languages and terminologies, but also perspectives and objectives of the different domain experts, addressing the composition and decomposition of the system and its elements, and running the development process up to implementable objects. Here you can clearly see that we are moving in the knowledge representation from the highest level of business domain knowledge representation using the different domain ontologies and mapping them using top-level ontologies towards the enterprise knowledge representation in IT, deriving the information models to represent the different IT processes, and finally defining the data models to implement the artifacts. This includes to extend the interoperability levels from the technical interoperability we know towards knowledge sharing at business concept level, cross-domain cooperation, and also skill-based interoperability, knowledge sharing in individual context. And this means interoperability is not first at all the matter of ICT domains, but the user domains issue. We have to share knowledge and skills built on a system, hierarchical system of ontologies. We have to advance the ecosystem from data exchange to knowledge sharing paradigms using an architecture-centric approach to the domains. And this is solved by a system-oriented, architecture-centric, ontology-based and policy-driven architecture standardized in ISO 23903. Thank you.
Hello, everyone. My name is Vaishakhi, and I want to talk about the iCare prototype system that we developed here at the Carolina Health Informatics Program. Computer interpretable guidelines are clinical practice guidelines that are implemented in computable form and interfaced with hospital health systems. They can be used to provide real-time guidance to clinicians at the point of care and have been proven to reduce costs and improve outcomes for patients. However, an issue with current commercial systems is that these solutions are not integrated with the electronic health record systems, which means that while they do provide guidance on how the treatment flow should proceed, they don't necessarily provide the clinician with information on what the patient's status is and what the patient's symptoms are, which they actually also need to make those decisions. This means that the clinician has to search for this information in the EHR separately, and that's an additional burden for them and may not fit well with clinical workflow. Our solution to this is the iCare system, which not only hopes to provide the clinicians with guidelines on how to treat the patient, but also to center and prioritize information about the patient that they need to make those decisions. And we do this by process mining through the structured EHR data and by using information retrieval and natural language processing techniques to get information from clinical notes, free text notes. And by using all of these sources together, we can provide the clinician with the information they need to make those decisions. As an example, consider this flow chart that is used to treat someone, which talks about the treatment that a person would go through for a certain type of breast cancer. This flow chart is broadly divided into decision nodes and process nodes. The decision nodes correspond to the key decision that the clinician makes at different points in the patient's care, which determines how the care should proceed at each point. And the process nodes talk about the actual care that the patient receives at different points. This flowchart is designed to be interactive so that clicking on each of these nodes, the clinician is directed towards different pages that gives them the information associated with each of these nodes. As an example, if they clicked on this particular node, which talks about neoadjuvant therapy or treatment that is given to a patient before their surgery, then they will be taken to a page that talks about all chemotherapeutic treatments that were given to the patient prior to their surgery. In this way, they are able to access all information related to the patient's treatment by clicking through these different nodes, and they can also be informed of the patient's current treatment status by understanding what treatments have been completed and what not in this structured format. This information is relatively easily obtained through billing data. However, when we think about the decision nodes, we need to look at the free text clinical notes, which is where the information is kept. As an example, consider this particular node, where the clinician needs to determine if the patient should receive surgery or not, and that really depends on how large the tumor size is. This information is included in imaging nodes, such as mammograms and ultrasound, and by designing appropriate search queries, we can retrieve these notes and present it to the clinician so that they can actually make their treatment decisions. In this way, we have designed a prototype of a system that not only guides the clinician through their treatment workflow, but also gives them the information that they need to make those critical decisions. Thank you.
Good morning, everyone. My name is Dr. George B. Jacob, and I'm an obstetrician gynecologist in Chatham Health Alliance in Chatham, Ontario, Canada. The use of BPMN, or Business Process Model and Notation, in curating clinical artifacts has been very exciting for clinicians such as myself, because it allows us to be both subject matter experts as well as the creators of these computable artifacts. However, when I went to access the tools required to create these artifacts, I found that often there was a paywall or there was significant server-side setup that was needed. I just wanted a plug-and-play option. So this project describes my journey of how I use Google Sheets as well as other online free resources to be able to achieve the same goal. BPMN.io is a website that is created by Commenda that allows people to freely create BPMN process diagrams. However, underneath the BPMN diagrams is XML metadata that can be then used by Google Sheets in order to create an executable REST API endpoint. We use Google Sheets because it allows you to have access to a server-side language called Google Apps Script, which will take that metadata and expose it as a REST API endpoint, as well as to create an online web app. So this allows users to use a web browser or a REST client like Postman or a Smart on Fire app, or as I mentioned, just a regular web app in order to run their process diagram. And the response that the server gives you back is a phrase that a clinician can then just copy and paste and put it into their EMR, thus saving them time for documentation, giving a reference for the clinical practice guideline that they used. And it also allows for analytics to be done down the road because it's structured text that's within these documents. So we use Google Sheets because it's free, it is familiar, and it is very scalable. All you need to do is have a Google account, and you can just save as a couple of Google Sheets files, and you will be able to create your own artifacts right away. I hope that you'll be able to join me for my breakout session where I describe many other features here, and you can also use that QR code to access the GitHub repository for all the source code for this presentation. Thank you.
Greetings. This is Alan Flynn from the University of Michigan Department of Learning Health Science and the Knowledge Grid team. And this lightning talk is about lessons in going for CBK fairness, where fairness refers to making CBK findable, accessible, interoperable, and reusable. Here we'll look through an architectural lens and think about 5 different types of systems that can help us create a CBK ecosystem and achieve CBK fairness. The first 3 of these items come directly from the digital object architecture of the DONA Foundation at dona.net, and they are identifier systems, repository systems, and registry systems. Of course, this is computable biomedical knowledge, so we need to add compute systems into this architecture, and we'll take advantage of search engine systems as well. Let's take a look at these in a little more detail. First, for CBK identifier systems, there are a number of choices. We've worked with something called archival resource keys on the Knowledge Grid team. You can get more information about those at arcs.org. We value ARCs for their unlimited ID minting capabilities because we can link any metadata that we choose to our ARC IDs, and for something called suffix pass-through, which allows us to take one ID and use it to identify whole objects and parts of objects. For a repository system, over the past couple of years, we've taken advantage of GitHub. Of course, GitHub is proprietary, but it's free for basic use, and it helps us manage code versions and releases very nicely for our digital objects carrying CBK. Plus, it has its own search capabilities, and it can feed data to our search engines on the web. There are other repository systems to consider, such as the Fairdom Hub in Europe and AHRQ's CDS Connect repository. For registry systems are important in this architecture as well for accessibility and helping people find things. We've worked a little bit with something called name to thing. Here we can put metadata and we can put our persistent IDs and link them to changing URLs, making sure that people can always find the digital objects that we create. So this is an access and find story. There are other solutions, of course, in this registry space as well: Perl, Cedar, EasyID, and others. And these systems can also feed their information to search engines. And finally, we're interested in compute systems. Here we give just one example. There would be many other examples of these. We've used APIs to drop computable biomedical knowledge from our digital objects directly into browsers. We do that using the Open API service description specification, JavaScript code, and any modern browser. Thanks for letting us share these architectural ideas with you. We look forward to learning from your ideas as well.
I'm Michaela Heigl, and I'm the Chief Digital Product Officer at NICE. In this lightning talk, I will be speaking about the collaboration NICE is organizing to explore the implementation of computable knowledge standards. The National Institute for Health and Care Excellence is the authoritative source of evidence-based clinical knowledge for the NHS in England and Wales. Its 5-year strategy has identified the need for a shift from words to data and to a more modular approach to recommendations. A key success factor is having guideline recommendations produced in an interactive, digitalized format. NICE has worked closely with the MCBK UK group since it was formed in 2019. In 2020, NICE established a content advisory board to help it move towards the strategic digital aims. MCBK UK has proposed a collaboration or hack day to activate industry involvement and understand vendor capability and willingness to adopt international standards for computable knowledge. The aim of the collaboration is to explore a range of technical approaches to transition NICE towards production of natively digital content for education and standards-based computable decision support. The objectives are to bring together relevant stakeholders, to demonstrate a selection of use cases, knowledge types, usage patterns, integration options, decision types, and technical standards, and to educate the stakeholder community, generate new ideas, and assess the relative merits of a variety of methods. The event will feature several clinical scenarios that are currently being refined. The plan is to have 2 in-person collaborathons in November and February. Both events will be multidisciplinary, but with some tasks that are primarily clinical and some that are primarily technical. Before the first collaborathon, we will develop online tutorials on prevailing standards and clarify the clinical use cases. Before the second collaborathon, we need to build the requisite infrastructure and prepare synthetic data. We are recruiting clinicians to participate along with invited vendor teams. We look forward to sharing our learning with the global MCBK community. Thank you very much.
Hi, my name is William, and I'm here to talk about operationalizing text-based clinical practice guidelines as computable decision support on blockchain. So this work was motivated by an IoMT scenario, or Internet of Medical Things, where personal health devices, such as Bluetooth-enabled blood pressure cuffs, glucometers, continuously measure health data. And this has a number of applications, as shown here. So as a secure computational framework to record and analyze this IoMT health data, we chose to use blockchain because of its trustless environment, by virtue of its consensus mechanism, its distributed ledger, which means there's no data fragmentation across different systems. So by using blockchain, we take care of recording and integrating the data, but what about analyzing the health data? Right, this requires clinical decision support features, or CDS. This has not received much attention in blockchain. So to fill this gap, we mobilized clinical knowledge found in so-called clinical practice guidelines, or CPG. Now, these are text-based PDF documents that aim to guide primary care physicians in evidence-based diagnoses and treatment of certain illnesses. So we use smart contracts to operationalize the knowledge in these CPG. So smart contracts are small software programs on blockchain to automate and validate interactions, such as financial transactions or enforce business and legal contracts. So in the first step, we capture the decision logic in the CPG using so-called computer interpretable guideline models, or CIG models, such as Proforma, Glyph3, Clean. So these are existing models. And then we convert the CIG model, which is a declarative model, into a smart contract that is written in an imperative programming language, such as Solidity. So in particular, we have a graph-based code generation approach that leverages a domain ontology. We are currently limited to rule-based CIG models. So a parser first extracts rule graphs from the CIG models. Then a converter converts these into intermediary abstractions for imperative programming languages. Then finally, a code generator spews out blockchain code, in our case in Solidity. So we've performed a preliminary evaluation. We found that recommendations were consistent between the declarative CIG model and the automatically generated smart contracts, insignificant execution times. Although the contracts were executed on the sidechain, we feel this shows the feasibility of our approach. There's many limitations to our work. It's quite preliminary. NRE properties, or rather, there's limited support because of the technical limitations of Solidity. We are currently limited to rule-based CIG models. These need to be structured as directed acyclical graphs. Rules need to be recursive, cannot be recursive, and need to be existential, for instance. And that's about it. Any questions, please feel free to reach out. Thanks.
Hi, everyone. My name is Dr. Rob Coram. I'm the Chief Medical Officer of Penda Health in Nairobi, Kenya. And I'm excited to tell you about why I think decision support for primary care in Kenya is really the ideal setting to try to implement clinical decision support tools. So guideline adherence in low and middle income countries is really shockingly low at less than 50%. Those middle bars that you see on the graph there, which is from Kenya Ministry of Health data, show that in 2012, guideline adherence was only around 30%. And as recently as 2018, that only really improved to slightly above 40%. And it's important to know that non-physician healthcare providers provide the vast bulk of primary care in Kenya and in many other low and middle income countries. And they really take care of a massive range of conditions. They're taking care of infants and pediatrics and adults, non-communicable diseases like hypertension and diabetes, trauma and pregnancy, and many other things. Many of the facilities are overburdened and under-resourced, and so there's little time and resources for training or for clinical oversight. At Penda, we've developed a clinical decision support tool, which we think is the right tech for this particular setting. We have Kenyan clinical officers who provide all of our healthcare, and they're supported by clinical decision support in more than 90% of the visits that we have at Penda. That's led to 82% guideline adherence across all of our branches, and of course, very happy patients at a much lower cost. This is the front end of our clinical decision support tool, which is in our cloud-based electronic health record. And it takes inputs in the form of complaints and diagnoses, and it gives outputs, which you're seeing here for an input of type 2 diabetes. You're seeing various outputs, which could be lab tests, imaging studies, prescriptions, patient education tools, and others. Clinicians must act on these suggestions by either accepting them or rejecting them before they're able to move on in the visit. Then we have dashboards on the back end, which allow frontline staff to review guideline adherence in real time. This can be viewed over different time periods across different branches and even down to the provider level. We're able to see which guideline suggestions were accepted or rejected on a very detailed level across the whole organization. So what I'd like to leave you with is that when considering how to implement clinical decision support tools and get the most bang for your buck, consider doing them in primary care settings, using non-physician healthcare providers, in settings where the baseline level of quality is low. If you're interested in this and you'd like to get in touch, I'd love to hear from you. My email address is there. Please be in touch. Thanks.
We have many people coming together to realize the grand vision of mobilizing computable biomedical knowledge. But how do we achieve interoperability on a massive scale? Perhaps with interoperable metadata, but there are many different ways of expressing metadata. A common metadata framework in this context is defined as a generic schema or data structure representing a transfer point between specific data structures, specifically to facilitate data conversion between the data structures. Consider the situation where we have 7 different data structures. If you wanted to convert from any of these structures to any of the other 6, you would need to build 42 distinct data conversion tools. What if we had a common metadata framework to use as a transfer station? To convert to and from the common metadata framework, you would only need 14 data conversion tools instead of 42. Let's look at an example for a single data element representing John Smith as a secondary author. With the RIS data structure, this is represented as an element named A2 and a data value of John Smith. Simple if you know that A2 means secondary author, perhaps too simple to use as a transfer point for hundreds of other data structures. Here is FHIR citation data structure. There's a cited artifact element containing a contributorship element, containing an entry element with an instance that contains a contributor element with a display element with the value John Smith, and a role element with a coding element and all the details for fully structured coding of the role as author, and a text element to express secondary author. Well, that works for deep representation of citation data, but perhaps that's too complex to use as a transfer method for hundreds of other data structures. As we model a common metadata framework, we have a top-level element of contribution with an agent element that contains who with a label of John Smith, role with author, and related role with secondary author. Perhaps this is an optimizing pattern, balancing the simplicity and complexity that we need for a common transfer station. The current draft specification of a common metadata framework has 146 total elements. There are 21 top-level elements shown here organized by their ability to support findability, accessibility, interoperability, and reusability, and also trustability, which was added by recent work from MCBK authors to categorize metadata to help mobilize CBKs. To learn more or participate, you can follow the project link or join us in our weekly meetings at 11 a.m. Eastern Time on Tuesdays. And here's my email address if you have any questions. Thank you.
Welcome to this presentation on sustaining open educational resources for you, the computable biomedical knowledge leaders. I'm Dr. Deborah Swain. My partners are Chris Cunningham and Nige Brown, and we're from North Carolina Central University. We have some challenges in making sure we provide good OER learning modules for you. We want you to know about learning based on a pilot that we did and having good OER resources to develop an international community. This will truly be an open resource for you. Leaders will be those who've been knowledge managers and library and information science professionals, as well as developers, wherever you're coming from, and will sustain the OER with narratives and stories that you have and can share. Here are some of the materials that will be available, starting with the manifesto from 2018, articles, slides, and looking at number 6, how to do good, strong, systematic reviewing, both for things that come to the repositories and also for making this gap that you see illustrated here. The LHS continuous cycle has a gap between data to knowledge and knowledge to performance. However, as you and I know, it's going to be much faster without having to go through printed articles. But how do we really do that? And as a sense-making group looking at gaps, which Brenda Durbin has described for years, we're going to close those gaps. Use FAIR as a principle, findable, accessible, interoperable, and reusable materials, and help with the infrastructure for the metadata, including designing a framework. How are you going to do it? Again, learning to evaluate articles before they come, and once they're in, what you can do to help the gap, go across it, go bring it together with sense making. We'll also recognize bias and try to prevent that in algorithms and AI. We'll track resources from the National Library of Medicine. And as the last bullet says, we're going to expand our community of practice. Entrepreneurs, you are invited. In conclusion, we want to use, share, and improve the OER when it is launched in January of 2023. Please recruit researchers. We're going to show you how to be part of MCBK, grow and manage your repositories. We're going to have for the OER resources online at a website, a textbook, and we'll build on the presentations we're giving this year and next year. This is a list of my team and the partners from all across the United States, from the University of Michigan, as many of you are and know, all the way to the University of Arizona. This is a list of the 20 students who participated from December to January. We were funded by the IMLS, Institute of Museum and Library Services, a grant with supplemental funding from the southern region of the National Network of Libraries of Medicine. Thank you so much for listening. See you soon.
Thank you for the opportunity to tell you about implementation of the Right Decision Service, the National Decision Support Service for Scotland's health and social care. Our National Decision Support Programme aims to embed decision support as the norm for practitioners and citizens across Scotland. It has 3 elements: technology, people, and processes. In terms of technology, our Right Decision Service platform provides a suite of knowledge translation tools which convert guidelines and research evidence into computerized knowledge. These tools are used by knowledge managers across Scotland. They do not require any programming expertise. The computerized knowledge products are then delivered as web and mobile apps and integrated with electronic health records. This screenshot shows a set of alerts based on our National Polypharmacy guidance and created by the Right Decision Service platform. These high-risk prescribing alerts are triggered on point of opening the patient record. This screenshot shows a set of web and mobile apps providing access to local and national guidelines and pathways. These have all been created by the Right Decision Service and have high uptake and good feedback from clinicians. This screenshot shows a set of mobile toolkits delivering interactive, computerized algorithms, for example, for sepsis screening in paediatric unscheduled care, all created by knowledge managers with no programming expertise required. To support creators and users of Right Decision Service tools, we have a programme of leadership, engagement and training. We have decision support leads in each health board. We have a user community. We are working on a competency framework and programme of learning opportunities. The processes that underpin the Right Decision Service centre on continuous evaluation and improvement. We have a pipeline of safety and quality assurance processes. We have started work on an implementation and spread framework to provide guidance on improvement methodology and on service model implementation. We also have an evaluation framework based on a logic model, which assesses impact at the level of usage, user satisfaction, practice change, and contribution to service and healthcare outcomes. This final screen shows evidence of impact at the user satisfaction level for our high-risk prescribing decision support. Majority of clinicians agreeing it supported patient safety and many examples of detecting clinical risk. Thank you.